Chapter 7 in your textbook, and it's Unit 6. I know that's a bit of an annoying. I'm going to call it Chapter 7 for the rest of the videos here. Is talking about trigonometric functions, and it's probably been a while since you've talked about trigonometric functions, so it's worth doing a little bit of review at least. I am going to go over the first quadrant of the unit circle because it is kind of the bare minimum of what you need to know in order to deal with trigonometry. One important kind of distinction of calculus versus 30-1 is in calculus, we fully embrace the radian mode. Every question we do is going to default to radians. If it specifically tells you to work in degrees, you can work in degrees, but we are going to focus on radian angle measures because ultimately they are much more mathematical. So there are 5 points in the first quadrant. There's the point at 0 radians, which is 1, 0. There is the point at pi over 6 radians, which is root 3 over 2, 1/2. There's the point at pi over 4 radians, which is equal to root 2 over 2, root 2 over 2. There is the point at pi over 3 radians, which is 1/2, root 3 over 2. And then finally, there's our pi over 2 point. So the point at pi over 2, which would be 0, 1. Now, every other quadrant on the unit circle, we can use this to determine, what that actual coordinate would be by reflecting in the x to the y axis. And the one thing I would like to point out too is that on our unit circle, y is equal to the sine of our rotational angle, x is equal to the cos of our rotational angle, and y divided by x is equal to the tan of our rotational angle. And we'll certainly use that as we work through chapter 7 in the textbook, but at least to begin with, we're going to approach kind of maybe a bit of a simpler concept, which is some limits of trigonometric functions. And I know when I say limit, a lot of students think, man, this is going to be rough, but they're actually not that bad. So to talk about this limit, it's actually pretty useful to have the function itself. Kind of weird, but we are going to draw one period. We're just going to draw it from negative pi to positive pi. And if we look at the sine function, the sine function would look something like that, from negative pi to positive pi. Now, looking at this limit, we're going to examine the limit from the right and the left. So the limit as theta approaches 0 from the right, and the limit as theta approaches 0 from the left of sine theta are actually equal to each other. And I didn't mean to put that equal sign, sorry. But the limit as we approach 0 from the right is 0, and the limit as we approach 0 from the left is 0. Therefore, the limit as theta approaches 0 of sine theta is 0. Now, cos theta has a bit of a different story. It's a dramatically different graph. It always looks strange to draw cos theta, I find, but we're going to do the same interval. So positive pi on the right, negative pi on the left, and the graph of cos would look something like this, where this is positive 1 and this is negative 1, just like your sine graph. So using that same concept, the limit as theta approaches 0 from the right of cos theta is positive 1. The limit as theta approaches 0 from the left of cos theta is positive 1 as well. Therefore, the limit as theta approaches 0 of cos theta is 1. And, both of those limits could have been done by substitution, right? There is no real issue with just putting 0 in for theta for either of those limits, but it's important to remind ourselves of the left-hand, right-hand limit concept. Where this becomes much more important is this particular limit. It is the limit, and I'll write it in big kind of angry letters here, as theta approaches 0 of sine theta over theta, which if we do substitution, is the sine of 0 radians over 0 radians. Oh, I was going to draw theta there, sorry. That's the sine of 0 radians divided by 0, which is 0 over 0. This is an issue. 0 over 0 is indeterminate. It doesn't give us enough information for us to evaluate the limit. Now, we have done this limit process plenty. I am going to immediately give you the values of the table, but what I do want to recognize, at least somewhere on your notes, is that this left table of values is the limit as theta approaches 0 from the right. My right limit of values is the limit as theta approaches 0 from the left. Maybe I should have moved those tables, but it doesn't particularly matter. So I'm going to just put this into my function. Keep in mind that when you're doing this on your calculator, you would have to type the sign of bracket theta, close the bracket, and then divide by theta. Although, sorry, you would have to use x in your calculator. Your calculator won't let you use theta. So I'm just going to put x divided by x there. You would have to check and make sure that you are in radian mode. right? Technically, this will also work in degree mode, but we want to default to radian mode when we're doing calculus. So as I approach 0 from the right, I'm going to put these numbers in. I get 0.998334, 0.999583, 0.999935, 0.999983. Now, looking at this, it appears that these values are approaching +1. I hope we all agree with that, right? The .999s are just getting larger. Sorry, not larger. They're just carrying on further and further in the actual limit process. It's worth mentioning that, sine theta over theta doesn't have even symmetry, so we can't just kind of make that assumption. But what we see, sine theta over theta does have even symmetry. It's sine theta that doesn't. It does ultimately, and these numbers are actually the same. And a lot of students struggle with the idea that even though 0 over 0 is certainly indeterminate, in this particular case, by using a numerical technique, we can actually identify that this limit has a value. And the reason we can do that is because both of these tables show that as we approach 0, sine theta over theta actually approaches 1. And we can make the statement that the limit as theta approaches 0 of sine theta over theta is equal to 1. This is a very important limit property. It's something you'll exploit in a lot of different calculus classes, and unfortunately, it is something that you need to memorize. And then really what the rest of these notes are going to be actually using that and manipulating it to solve different problems. The one thing I would caution you is it doesn't have to be theta. If you had sine x over x as x approaches 0, that would still be true. So we are going to use this to deal with different limits along the way. Now, immediately, the first issue here is that this has nothing to do with sine theta, right? Or at least it doesn't appear to. What we have to look at and exploit is the fact that tan theta can be written as sine theta over cos theta. So the first thing I'm going to do here is I'm going to rewrite my limit as the limit as theta approaches 0 of, and I'm going to write it as sine theta over cos theta multiplied by 1 over theta. And that is the same statement as I did above. We can write, and I'll put over here, that tan theta divided by theta is tan theta times 1 over theta. They would simplify to the same thing. What I'm going to do then is I'm going to kind of mix and match my fraction. And I'm going to say that I'm going to write this as the limit as theta approaches 0, and you guessed it, of sine theta over theta times 1 over cos theta. Now, what that allows me to do, if you remember back, and it's been a while since we did this, but we can use the product property of limits, and I can rewrite that limit as the limit as theta approaches 0 of sine theta over theta multiplied by the limit as theta approaches 0 of 1 over cos theta. Now, part of the reason why I can get away with this is that in my second limit there, cos theta is not 0 when theta is 0. And more importantly, we now have the ability of saying this limit is equal to 1. We know that. That's the property that we're exploiting today. The other limit can actually be done by substitution. That limit is 1 divided by the cos of 0. The cos of 0 I'll put over here is equal to 1. That's the x-coordinate of the terminal arm at a rotational angle of 0 radians. And so what we end up with is 1 times 1, which is just 1. So we've proved that limit or shown that that limit is equal to 1. All right, I think I'm going to do one more, and then I'm going to split the lesson into 2 here. And really what it is a lot of these questions end up being trying to manipulate the question into that form of sine x over x. Now, I caution you though, if this limit is not equal to 0, you wouldn't use this technique. But you'll see that these questions are typically presented this way. I want to get to the point where somewhere in my question, I have the limit as, be it theta or x, doesn't matter, I'm going to use theta, as theta approaches 0 of sine theta over theta. And most of this lesson is trying to remember or jumpstart our brains to all of those limit properties we used as we were, exploring limits in chapter 1. So I am going to rewrite the limit as, the limit as x approaches 0. And then inside that limit, I'm going to move that 2 in the denominator and write it as 1/2. And the reason that I'm doing that is in order for this technique to work, these two expressions have to be the same. They weren't right here. The numerator or inside the argument of that sign was x, and then the denominator was 2x. Now, the benefit of remembering our limit laws is that we have the constant multiplier rule. So I can take that constant out, and this is equal to 1/2 times the limit as x approaches 0 of sine x over x. This is our property. So this becomes 1/2 times 1. So my answer is 1/2. All right, that's part 1. We're going to do some more manipulation in part 2, and then, of course, get to the assignment.